Hi, folks. Let me get this started. It is my pleasure to introduce Colloquium speaker today, Professor Heather Lewandowski. When one of our own gives the colloquium, there's often not really all that much to say. You all know about Heather's many research accomplishments at JILA in AMO physics. I would like to say a couple of things about possible roles of Professor Lewandowski that maybe not everybody knows. She's Associate Chair of Physics as the Director of the Engineering Physics Program. She's also the Faculty Director of the Qubit Quantum Education and Workforce Development Program. So Qubit is a large initiative at CU that basically brings together folks from CU Physics, JILA, NIST, and local companies. And it does all sorts of efforts in quantum sensing, quantum communication, quantum computing. And Heather is the faculty director of the education and workforce development side of that. Things that you might also not know is that Heather has won many teaching awards, including outside of physics, the Boulder Faculty Assembly Teaching Award. A year or two ago became one of the system-wide presidential teaching fellows, and also a few years ago won an AAPT teaching award. And these awards cite many things, because Heather's an awesome teacher, but often the citations are about her work on helping students in laboratory and or research settings, which leads me to another hat that Heather wears that, again, many people know, but not everybody, is that Heather is a leading PER researcher in the country. She was the director, the president of the ALPHA organization. What does ALPHA stand for? It's the Advanced Lab Physics Association, which is a national organization of faculty who think about upper division labs. Heather has done many lab reforms here at CU, starting many years ago in the junior lab area, and then did major work with education research and curriculum, complete redesign of the 1140 freshman lab. She is currently working on something similar in the sophomore 2150 lab, which many of you may have gotten emails about. So if you have questions about that, you may want to talk to Heather about it separately. And just at the time of the pandemic, when the major transformations in Phys 1140 were no longer really feasible, when students were not able to come in, Heather did it again and transformed 1140 into essentially an undergraduate research experience rather than an undergraduate laboratory experience. And that leads into today's colloquium. We're going to learn about what she did, why she did it, how she studied it. I have one last thing to mention. We were talking about this beforehand. So as a PER researcher, Heather has supervised many postdoctoral researchers in PER. Some current ones are here. And I believe that Heather may lead the nation in the number of postdoctoral PER researchers who she has mentored, funded, and supervised. So it's kind of an awesome accomplishment. Let's welcome Heather for colloquium.
I've done this before. Awesome. Thanks so much, Steve. Yeah, I'd like to tell you a little bit about the project that we worked on, bringing undergraduate research to 1,400 students and how the science that came out of that and the student experience that we had over 3 years. So when we think about undergraduate research experience, I think here it's a very prominent thing of our undergraduate program. We really encourage students to get involved in often traditional undergraduate research experiences. And there's some good reasons for that. There's been a lot of work looking at the benefits for students, right? Think about developing teamwork skills, sense of belonging, persistence in STEM, some cognitive benefits in terms of how to think about research and self-efficacy. So there's a lot about why undergraduate research is great, but what is often not sort of acknowledged is the limitations. The idea that there's sort of only so many positions available, right? We have like 650 undergraduate students and about 60 faculty. So there's limited positions in our department. And also, this sort of model really excludes some students who maybe aren't able to take a summer off from another job or carrying responsibility to really participate in undergraduate research. So it really limits students' participation in some way. So if we think about this, it's great, but we're limiting, what is a solution? And I say one proposed solution to this problem is a cure. And so that's what I'm going to talk about today. So what is a cure? It stands for course-based undergraduate research experience. So this is a research experience done within a typical course that students take as part of their curriculum. It has sort of 5 different components of what makes it a cure. First is that students have to use scientific practices, right? So engage in typical scientific practices, whatever it is for the discipline. In addition, there has to be some sort of discovery. This isn't about just confirming that little g is 9.8. It's important to a community outside the classroom. This is a key component. It's not just interesting to the students or the instructor within, but outside. This could be the community, the local community, or the scientific community. Somebody outside the classroom has to care what's going on. Collaboration is a key of the cure and is a key of science, right? Is not just sitting alone doing work. Collaboration is a key of a cure. And finally, this idea of iteration. Famously, nothing ever works the first time, right? In any science, and you have to iterate, and that's a key component of a cure as well, unlike sometimes a more linear process that we have in other sort of experiences in labs. So if you think about all of these, right, in isolation, right, you see these things in sort of typical lab courses. It's really the combination of all of these together that really makes a cure, right? It's the integration of these components what we're doing here in the cure environment. So if we think about how we compare a cure to maybe a traditional sort of lab experience, maybe a little bit more open-ended inquiry-based lab where you have a little more student choice, a cure, and then sort of traditional undergraduate research experiences. This is sort of the full spectrum of the kinds of experiences students get at the undergraduate level. If you think about how to compare these, well, first is in the level of guidance, right? In traditional labs, they're highly guided, can be very prescriptive. Step A, step B, step C, as students follow. Inquiry-based labs, right, remove some of that guidance and allow more student decision-making. Cures have sort of a little bit less of that in a course. In a traditional undergraduate research is an apprenticeship model, right, where either a graduate student or a postdoc or faculty member has that sort of apprenticeship, mentorship relationship with an undergraduate. If we think about kinds of results that come from these different experiences, right, in traditional labs or even inquiry, we know the answer, right? There are previously established results that we're ultimately trying to get. In cures and in traditional UREs, right, we don't know. That's the whole point of research, right? We don't know the answer. We're trying to search, make that discovery. So that is another distinguishing characteristic. And then finally, in terms of the scalability, traditional labs and inquiry lab, very scalable. So, 1140, 450, I think I've taught a class as big as 750 in that course. Cures are somewhat scalable, and we'll talk a little bit more about that. And then traditional UREs, really quite limited, right? It's an intensive experience. We can only offer so many of these positions. So these are sort of the range of sort of benefits and challenges if you think about a cure. One way I like to think about this is there's a full spectrum of these things, and you're really trying to balance this idea of how authentic the experience is in terms of real research as compared to how much resources it takes, sort of the messiness of the process, right? Is it very ordered? Do students all come in and plug cable A and right? It's very nice and ordered, and sort of the complexity of the system. And so it's a matter of balancing these things. There are trade-offs to be made. I'm going to argue that in certain cases, cures can be really powerful, and it's worth the messiness. So if we think about, well, if we have all these trade-offs, is there really enough benefit in a cure to really pursue these things? And so there's been a lot of research looking at benefits. And these are sort of outside of physics, particularly in chemistry and the life sciences. But the recent NASAM report looked at students persist in the STEM major due to the cures. They have increased self-efficacy. They increase their technical and analytical skills through this process. And they really help to clarify their career direction by participating in these cures. Additionally, there's reduced barriers to participation, and this is a key component, right? It's integrated into students' curricula. They don't have to do something outside. This satisfies one of their degree requirements. It doesn't require additional time or summer work, right? For folks who just don't have that available within their schedule or in the summer. And finally, there are no GPA requirements. You just sign up for the course, right? There aren't these sort of barriers to participating because there are limited positions. So there are similar benefits to undergraduate research, but there's also reduced barriers. So that seems like something we should think more carefully about. So the context of the work that I'm going to tell you about today was that our team designed and implemented the first ever large enrollment physics cure. These cures have been done a lot in chemistry and biology. I think there's good reason why they haven't been done in physics, but we can talk more about that. In particular, it was really driven by the need to go to remote courses in the summer of 2020. In May of 2020, I was supposed to have the semester off, actually, from teaching in the fall. But that wasn't going to happen, and Mike Dubson asked me, so can you teach 1140 and do something with it? We've got 500 students, got to do a lab experience. So there are two options. One was to go to maybe either simulations or sort of at-home labs. There are various things that were tried across the country. And I don't know, we were sort of naive at the time, like, ooh, this is an opportunity to do something bold. Let's try doing a cure. It's always been on our radar, but we really hadn't had the opportunity to do it. So we thought, oh, let's do this in the fall. And so that's sort of the context of this, because I think that's important. Because of the current situation of where we're in, we had particular challenges and motivations for why we did what we did. In terms of motivation, our team decided that we wanted to really teach research skills in particular. We wanted to foster a collaborative environment that was particularly important early on in the pandemic. And we wanted to provide this authentic and motivating experience. We wanted this class to be really useful and motivating for our students. However, we had serious constraints. The smallest semester we had was 450 students. It was at the first year level, introductory level. We had limited time to create. We had some time over the summer, right, when we're all still in lockdown. It's just a 1 credit course, right? So how much can you do? I was told I have $0 to do this. Needed to be completely remote. I say run from 2 to 3 semesters. We did not believe that at this time. We thought, oh, we just need to get through the fall. We'll do this for 1 semester. Well, it ran for 3 in the end. And importantly, it needed to be accessible both in content for our introductory students, but also in terms of technology, right? You have to think back of in terms of internet and computing and all of that going on in fall of 2020. So this is sort of the backdrop for what we had to deal with. So if we think about all of that, we wanted to do a cure, and we have all these different components that go into actual research, right? From reading previous studies, peer review, results, plan analysis, form research teams. These are all these sort of general components. We couldn't hit all of them, mostly due to the sort of pandemic issues, but we were able to do all the ones except these 4. Determined research question was really a limitation of having 450 students, right? But we couldn't really have them design and build the apparatus. But we were able to achieve all of the rest of the activities. Okay, so that's what we wanted to do. Now, we need a research question to answer, right? And we had a variety of different constraints that we wanted for our research question. The first is we wanted a local connection to a principal investigator. We wanted to have that connection to CU, and in particular, a local connection. We also wanted the question to really require all of the student work. We didn't want this to be like, well, yes, I could just write this quick algorithm and do this research. We wanted a problem that actually needed thousands of students to participate in, and amazingly, we found one. We wanted the question to be interest to the scientific community, right? This is a key component of a cure. And really, anything outside the classroom, we chose the solar physics community. And finally, the analysis had to be possible for intro physics students who may have never had any sort of lab course, any programming, any sort of solar physics before. So that had to have a question that could really be tackled by those students. So we ended up finding Dr. James Mason here, who at the time was down the street at LASP. And he's a solar physicist and looking a lot at solar flares. If you think about the sun, there's kind of two major sort of unknown sort of frontier questions that folks are trying to answer. And one of them is, why is the sun's corona so hot? So the sun has a photosphere, which sort of, think of it like the surface of the sun. It's about 5,000 or 6,000 Kelvin, relatively cool. Outside of that is the sun's corona, and it's about 1,000,000 Kelvin. This is very odd. It's like, right, you have a campfire, and the further away you go, the warmer it gets, right? How is the corona so much hotter than the surface of the sun? This is a fundamental question that many solar physicists are writing grants to NASA to try to answer. And so there are multiple possible explanations of what's going on. In particular, there are two dominant possible mechanisms that we were trying to think about eliminating. One is nanoflares, and the other is Alfvén waves. So nanoflares is the idea that there's a whole bunch of very small solar flares that are pumping energy into the corona. And that's why it's so hot. They're sort of unobservable because they're very small compared to the X-ray wave background, but they really are pumping heat into it. Alfvén waves are sort of magnetohydrodynamic waves that can also couple energy in. We were going to focus on nanoflares. The idea of, could these be the dominant mechanism? And so to be able to answer this, we had to look at how frequent flares were of different energies. And I'll show you a plot of how that works in a second here. So if we look at sort of previous studies of basically flares, flare frequency distribution. Some of these are our sun, some of our other stars. They're using a variety of different techniques and satellites. Here, oh, that is really far off. That is fascinating. So we have the frequency of the flares as a function of flare energy. And these are all the previous ones. You can see they've looked at different regions of in terms of energy. They've looked at sort of different stars and different satellites with basically taking these data. And the idea here is, if you look, this is a power law distribution. The number of flares as a function of energy should have a power law distribution with this sort of critical exponent of alpha. And it actually takes just a few lines to show that there's a critical value of alpha. If alpha is less than 2, nanoflares are not the dominant mechanism. If alpha is greater than 2, nanoflares dominate. One way to think of this is, if that slope is very high, bigger than 2, there's more and more nanoflares observed up here that really drive this energy. And so our ultimate question is to look and try to figure out that power law for our own sun using data from a spacecraft. So basically, students worked in Zoom, right, usually in breakout rooms for several hours a week, in teams of 3 to 4 to analyze GOES-15 X-ray data. So GOES is the Geostationary Operational Environmental Satellite. It's what tells us about our weather, right? So there are 2 of these up there at all times, east and west, and all those wonderful weather pictures, they take that. But they also have instruments that look at the sun, in particular the long and short X-ray region. And so students ultimately went to the Space Weather Data Portal. It's a database that has this publicly available, and worked with these data collaboratively using Google Colab. And so they would download data. They'd get to choose what data they wanted to download. This is in the long X-ray region. And it looks something like this. So here's the irradiance in watts per meter squared as a function of time. And there's various flares you can see popping up here. This in particular is an M-class flare. And so what students were doing is they would determine ultimately the total energy of that flare as a function of irradiance. So one key component of why we needed students, this is actually a very clean sort of spectrum, but often it's very complex where you have to first think about, well, there's some background X-ray flux that's going on. That depends on where you are in the solar cycle and what's going on the sun. You don't want to integrate that background flux. Additionally, when does that flare start and stop? Is that flare sort of overlapping with another flare? All of these sorts of things you can do by the human eye looking at the data and making decisions. Turns out people have tried various sort of machine learning algorithms and it's failed quite miserably. Previous to this, people did really sort of crude things where they said, oh, we're just going to integrate from where we'll find the peak, we'll go down to half, and then we'll draw a box and figure out what is the area of that box, right? So from our project, we were able to really go in and get an accurate determination of what is the integrated irradiance of that flare. And then the idea was to combine all of the analysis from each individual flare to look at the slope, look at how frequent flares were of a certain energy, and therefore, excuse me, come up with this power law distribution and figure out if the corona is being heated by nanoflares. All right, so how do we actually do this in reality? What were students doing? We modeled this just like an undergraduate research experience. What did they do? First, they did a literature review, read sort of parts of papers that looked at these kinds of flares. They learned the tools, so Google Colab in particular, and a little bit of Python, but not a lot. They formed a team. We had an entire week of the course dedicated to how to work on a team, how to deal with challenges of teamwork. So we took that part seriously. And then they developed a research plan, right? That's what we do. We propose a research plan that they got peer feedback on to iterate, right? We're building in this iteration component already here, where they would go into basically exchange people in different breakout rooms to present their analysis plan, their sort of proposal with others, and get feedback so that they could improve on it. So that was the first phase. Then they took that plan, and all students used their sort of proposed analysis on a test flare. So everybody used the same flare sort of as a baseline to really sort of test out their process. Then they got to go into this giant database and choose a flare. So across about 10 years. Basically, in the end, we looked over an entire solar cycle of about 11 years. Then they did the energy analysis. They once again got peer review, and they got to iterate on their analysis. Then we took the results from all teams, and then students were able to do analysis on that final data set that included sort of the energy from all the student flares. Then we had a research meeting, both pre and post, where they met with the PI, giant webinar. They got to ask questions of the PI. And then finally, their analysis was written up in a flare archive entry, which allowed us to eventually review those to include in the final analysis for the paper. And they wrote something called a memo to future researchers. Just like when you're in an undergraduate research, like you only have a finite time and somebody else is going to take the project on after you, you have to sort of let them know what was going on. And so the students wrote that memo to the next semester's teams to tell them where they had sort of gotten to and what the next semester was going to do. So here's the result. This is 3 semesters worth of data. Each one of those represents an individual solar flare that was analyzed by the students. So this is frequency versus total energy, and alpha is 1.63 with an uncertainty of about 0.03. These nanoflares are not the dominant mechanism. This is the largest study I've ever done. The largest study previously was 50 flares, and it was this sort of box integration. This is a big result. This is not just interesting for the students or interesting for us, but actually the solar physics community. In fact, this was published this past year in the Astrophysical Journal, Coronal Heating as Determined by Solar Flare Frequency Distribution Obtained by Aggregating Case Studies. So here the first author is James Mason. Colin West, you also all know, is a professor in the department. A variety of other folks. Courtney Peck was a previous graduate student in our department, is now down at LASP. And you see this where it says, show first author list, full author list? About 1,000 undergraduate students and graduate TAs participated and contributed data and analysis and intellectual development to this work. And so we're all included. I'm way at the end there. This was pretty exciting. So all students went through this process. They looked at the paper and opted in to be an author, and we went through this process of the reviews. It actually sailed through review quite easily. There were very minor comments, and so this was published. I will say that we asked ahead of time the Astrophysical Journal if they would accept such an author list. They said yes, and we brought down their server for about a week until they could figure out, yeah, we actually did sort of break it, but they finally figured that out of how to get this. So this was really an exciting result about thinking about the sun. So that's the sort of research component of the sort of the solar physics, but we also wanted to evaluate the impact of the course itself. And so we've done a lot of work since then, looking at development of skills, programming skills, analysis skills, how students thought about confidence in their ability to do research and affect. We looked a lot at teamwork. That was a big goal for us. Really surprising things about teamwork. One, there's a lot of people who feel like, oh, students hate teamwork, right? They hate working on teams, and that turned out not to be the case. In fact, one of the most positive aspects of this was teamwork. And I don't know if it was because of the time we were in, but we had many students who, for things beyond their control, had to drop all of their classes, but said, can I just be in this course because I don't want to let my team down. Right? I want to be a part of this experience. It was that sort of collaborative teamwork that was really impactful. 3 to 4. A lot of teams. We also looked at how their views aligned with experts of experimental physics and their thoughts about participating in authentic research. And so I'd like to tell you just a little bit about the results from our education research looking at these two particular components. So thinking a little bit about authenticity, we really had some big, broad questions. One is, did we provide an authentic experience for the students? I'll define authenticity in a second here. And then, to what extent did students feel that they were participating in authentic research? And when they talked about that, what components did they feel that they experienced? So from the student perspective. So first, just thinking about what authenticity means. So I take this from Rowland et al., where they say, basically, courses that, those that flexibly engage students in research practices while they work on a novel experimental question to produce potentially publishable data for audiences who are interested in the scientific outcomes of their work, right? So this is sort of a broad definition. If we think about really a framework that we borrowed from this group as well that we applied to our situation, think about all the components and how those align with the course. First is failure. How do we design and experience failure setbacks? Turns out you don't need to do this. This naturally happens in any course, right? This is challenging. This is research, right? I mean, my group in particular has felt this deeply recently, right? There's always this component. Iteration, this idea that they were allowed to go and talk with other groups and get feedback and iterate on their plans and iterate on their analysis, right? So that was built into the course. Scientific practices, right? They worked with, Python, Google Colab, doing a variety of analysis things. They did presentations and things like that. So we had that scientific practices component. Relevant discovery, right? This novel discovery, right? That was definitely part of it, right? It was real published paper. This idea of having decision-making power, ownership over their work, right? They were allowed to choose the different flares and how they analyzed, how they subtracted off the background. There are many different ways to do that, and they made those decisions. Collaboration is an important component, right? And that was throughout this entire course. They spent all of their class time working in these teams, essentially. And then finally, successful science, producing data results, right? Answering research questions. I would say, yes, check, right? They had a published paper. So based on all of this, considering what they did in the course, I would say, yes, we at least provided the opportunity for them to experience real research. But now, what did students think and what aspects of authentic research did they say they experienced? So one really quick overall, we used a lot of previously validated instruments. One is the URSA survey that was actually developed at CU in the ethnography and evaluation unit, which asked students at the end of the semester, how much did you engage in real world science research? And so from the fall, 94% said at least to some degree, did they feel that they did participate? Okay, that's nice. But why, right? Why did students feel this way? And what components had them feel this way? We really then needed to go away from the quantitative to understand what was happening until understand why. And so we used open-ended student responses to really build detailed evidence of what students considered authentic about their experience. And so, right, we use basically this memo to future researchers as our data source that they wrote at the end of each semester. And so I'll give you what the prompts were for students for this final assignment. First was describe the project in terms such that someone new can understand what we are doing. What are the research goals? How do we achieve them? Summarize what conclusions we can draw from our research results. Suggest ideas how this project could continue in the future. What should a new student be thinking about? What should their goals be for the research? And finally, discuss your personal experience. What did you learn from this semester? Do you have any advice that you would give about the analysis and working with collab, teamwork, etc.? The key component to these questions is that we did not ask directly about authenticity. This is important when you look at the responses. We did not ask them, we asked them about these questions. So to look at these, we use a process called coding. It's a way of tagging responses that align with this framework of authenticity. I'll give you an example because this is not something you might have seen before. The coding we used was directly connected to that framework. So the codes that we used, the way we tagged parts of the memos, included some direct authenticity. So when students said they did real research, felt like a scientist, or understood real research. There's more indirect authenticity when they talked about relevant discovery, the societal impact of their research, collaboration with scientists, not other students, but scientists outside of the classroom, and publishable science. And then the research components that we're tying to these ideas of authenticity, so practices, failure, iteration, that come from this idea of authentic research. So here is an example of where students are connecting these research components to this idea of indirect authenticity. So this is a quote from one of the student memos. Here's the thing, though. There are flares constantly occurring on the sun's surface. There are tiny flares and there are big flares. And then there are flares so massive that they have the potential to disrupt pretty much every electronic device on Earth. These are bad. Agreed. The goal of this project is to analyze the total energy output and how often you would expect it to occur. So this is an idea of a research component, right? This is the goal, this is the practice that they're doing. Then sandwiched next is this component of indirect authenticity. This will help scientists better protect the Earth because they'll be better able to predict the occurrence of dangerous flares and take the necessary precautions. And then we go back to research components. In this class, you will find, name, and analyze your own flare. That's the component that they're doing. And then we go back to indirect. Next fall, your data will be published in a real scientific journal. So you can see this back and forth between the components of what they're doing in the course and these ideas of authenticity. Here's just one other example, connecting now research components to direct authenticity. So here's an example. I learned a lot this semester, mostly about programming and the scientific process. You'll be doing some Python coding, nothing complex, but computers really help with the analysis of large data sets. I had experience from programming classes, but I had never done any data analysis. It was interesting to experience and learn about graphing and Python functions for data analysis. I also learned more about how real science is done. Spoiler alert, it's just a bunch of people struggling with code until it finally works and you learn something. Then you make a conclusion, submit it to peer review, and make edits as needed. I think we can all relate to that a bit, right? This is somewhat unusual for a freshman lab class. If we look at all of the memos, these are like several page documents. We went through and coded 405 of these from the first semester. Nearly 80% mentioned having participated in authentic research, right? So this suggests the majority of students felt like their research experience was authentic in addition to this quantitative component. And I think it's really important to note, right, that they weren't prompted. This was them bringing up these ideas within their memos, right? And so it's a testament to how this was important for them to mention to future researchers. So I would say, to a great deal, the students felt like they participated in authentic research. Not only to provide them the opportunity, but they understood that process. Now, what aspects did they talk about the most in these memos? So under sort of direct and indirect, the most common things were they use this word real research. They use that exact term. They also talked about relevant discovery or societal impact, right? Nearly 300 responses. So those are the kinds of things that they were mentioning most commonly in these memos. So we've done a lot of work on authenticity to show that students really had this idea of real research. We did a variety of other work that I'm just going to sort of highlight. We dug in more with qualitative, but I'm just going to give you the sort of snippets of quantitative around research skills, and then I'll talk more about views. So there was a unfortunately named survey, the persistence, I can't remember. The acronym is PITS. It's the PITS. And these are sort of for other cures. And so we use this for our own course. So here we ask them about teamwork. And so overwhelmingly, right, you see all of these are like well above 80%. So what did students agree with? Working as a team helped motivate me to stay engaged with the course. Working at my team during this course was fun. It helped me learn. Team problem solving allowed us to be more successful and conduct research this semester. While working with my team, I felt that my contributions were appreciated, and I was able to contribute to my team's success. I think instructors often are nervous about having students in teams and say, oh, there's just going to be so much student pushback and so many problems. I would say we didn't find that, right? And this was actually a bit surprising to us. But overwhelmingly, students felt that this was a productive environment. Along peer review, which is another component of science, right, we have nearly 90% agreeing that peer review comments provided useful information to help me revise my analysis. right? The act of peer reviewing helped me guide my own research, and peer review is an essential part of the scientific process. I'm not sure all of us would agree with Blue based on my experience, but this was, right, this idea of getting feedback from their peers. Really, they felt this as a productive and useful experience, and that we might consider how we build this in a productive way to our other courses. Views of research, thinking about, once again, fairly strongly, my findings of the research project gave me a sense of personal achievement. My research will help to solve a problem in the real world. My findings were important to the scientific community, and I was responsible for the outcomes of my research. They took that ownership of this. Once again, very positive outcomes. Digging more into this now, views of experimental physics, right? We have a validated assessment that we've run at CU and honestly all over the world. We have nearly 100,000 students who have now taken something called the E-class. It is 30 statements about experimental physics that students choose to agree or disagree with. Here's just an example. When doing an experiment, I try to understand how the experimental setup works. And then they're asked, what do you think when doing experiments for class? They can agree or disagree. And so what we wanted to do is compare this cure to the most recently transformed in-person experience that had happened sort of just pre-pandemic. And so this is the most technical component. Basically, we did an ordinal logistic regression where we controlled for course type, which says, is this the cure or the pre-cure? We looked at major, gender, and the pre-score. This is taken at a pre-semester and post-semester, so you can control for that covariate. And you can look, the outcome of a logistic regression or ordinal logistic regression is odds ratios. And so what an odds ratio says for something, say up at the top here, oh, that's 4. That says students are 4 times more likely to sort of agree with the sort of expert view if they were in the cure course versus the transformed course that was previous to that. So one thing to note is all the odds ratios essentially are 1 or greater, which means they're as equally likely, even though they didn't have that hands-on experience, to have that sort of professional view of experimental physics. Let me dig in to, say, the top ones here, which have the largest odds ratios. So what did students really have sort of the expert view on? First was this statement: communicating scientific results to peers is a valuable part of doing physics experiments. It's maybe not surprising. They actually had a lot of communication amongst peers about this during their teams. Physics experiments contribute to the growth of scientific knowledge. Maybe not surprising since they were doing real research and actually came out with a real result. Working in a group is an important part of doing physics experiments, right? The core component of the course was this team. Scientific journal articles are helpful for answering my own questions and designing experiments. This for intro classes is very unusual because you usually don't really get into this, but we had them read portions of scientific articles to base their plans on. And then it's helpful to understand the assumptions that go into making predictions, right? This last component here. So those all have the sort of the highest odds ratios, the biggest impact to the cure over the already inquiry-based transformed course. So this was sort of a nice result from the cure. So basically across the board, like everywhere we looked, we really saw really positive outcomes. Yeah. Oh, whoa. I don't remember. It's in the paper. I don't know. I don't remember. Yeah, so these are, 95% confidence intervals on these odds ratios. So I'd just like to leave you with a quote from a student. And think to yourself, if a student said this coming out of my lab course, how would you feel? Oops. Overall, this is from the Memo to Future Researchers. Remember that this class is a kind of how to science class. Right, so they're talking to a future student. The most important things you'll learn aren't how a solar flare works or how to write code. It's how to conduct good and meaningful science. It's how to ask scientific questions and work collaboratively. Just remember that this class is here to help you become a better scientist and to set you up for success in any scientific or engineering discipline that you may pursue. A freshman in our lab course said this. That's kind of powerful. That sort of quote really sticks with me. So if we think towards future work now, how can we develop models of sustainable physics here? This ran 3 semesters. We answered the research question. We're sort of done with that research question. And in particular, if we think here, can we create a sustainable cure for our modern physics lab course right now, our sophomore level, Physics 2150? A postdoc in the group, Dr. Rachel Merritt, has a fellowship to really investigate this question and also think about 2150, which lots of you have talked to us already, and we'll get an opportunity, hopefully, in a few weeks as well to talk about. So this was a massive effort, and I'd just like to really share how much work it took to put this together. So in terms of the course development, Dr. Alexander Worth was a Strobe postdoc. Colin West and myself were instructors of the course. On the education research side, additionally, Kristen Oliver was a graduate researcher and TA. On the astrophysics research, in addition to James Mason, Dr. Don Wodaraska and Dr. Courtney Peck, as well as Dr. Allison Youngblood, LASP folks, really contributed greatly to this process. Thank you. Yes, any questions? Mike.
How did you make the connection with James Mason and solar physics? You know, he didn't just come to your door and knock on you and say, hey, I need 1,000 students.
No, okay, reality is, this researcher right here knew Dr. James Mason, and I knew Don, because I sat right next to him working for like a year. That's my husband, by the way. He works at LASP. I started talking this idea. He's like, oh, James might have ideas. Go talk to James. And so that's how it started, somewhat serendipitously. Yeah, Olivia?
One thing that really caught my attention is this overwhelmingly positive experience of teamwork.
Yeah.
When I think back on my own undergraduate experiences, it's much more of a mixed bag than I think what you saw there. Any thoughts on what might have been different about this experience or framework?
Yeah. So some of the things I can say that might have contributed to that is, you know, we spent an entire week focusing on how to work in a team. If there are complications, we had scenarios that worked with students like, oh, if you come up with this, with like some students sort of social loafing in this context, like how do you approach that? Sort of the activity was really focused such that one person couldn't do it. It really needed a team effort to be able to do. And they had to navigate the teamwork roles, although they were given suggestions on how to deal with teamwork roles. And the fact that you have roles and you can switch them around. It's not just everybody or one person contributing. So some of those activities may have led to the outcomes. What have you two?
So this was designed to deal with COVID, and everyone was remote. And so how does the effect of being forced to be remote as opposed to mostly in-person contact coming up, how does that change the kinds of questions you can ask?
Right. I mean, we were quite constrained in this system because we couldn't have any hands-on, equipment and things. I think now it actually opens up more questions now that we can have folks working together in a classroom with real equipment. So I think it does actually open up a lot more opportunities for different types of research questions to be answered. David?
Yeah. The choice of team size of 3 to 4 is relates to the more, less, different problems, or
yeah. And we formed these teams, I will say, intentionally. So we had this pre-semester survey asking about different things like coding experience and various things. And there's been previous research on how to form teams, and we use that to intentionally form teams. 3 to 4 was a little bit practical. Like on Zoom, that seemed like a reasonable number. In terms of also the activities that they were doing, that was sort of, everybody could still contribute to it, but it wasn't overwhelming.
so in a post-pandemic world, would you have bigger teams?
depends on the project, I think, the scale of the project, and how many folks you really need to work on that in different roles. So I think it depends a little bit.
Just following up on that, I think that the will think you allow students.
We pick the teams. And I think of each, so we had, I don't know, we had, more than 100 teams each semester. And out of 3 semesters, we had 2 teams overall that were dysfunctional. We had to change up. So out of 300, I feel like that's much lower than I expected. So we originally started with some other things in terms of we wanted to make sure there was not just one non-male identifying student in a group, was another consideration. Kenna, and then you. It's been getting cited. So yes, so I think, yeah, I mean, NASA has been really interested in this. They've done their own sort of thing, but they've reached out in their sort of Heliophysics Week, have really sort of highlighted this research. So they've taken notice as well, not just 9 News. Yes?
So going back to the team formation,
Yeah.
was your intention to form the team for kind of heterogeneous experience or more homogeneous experience?
So yeah, we had talked to a lot of folks previous on this, and in terms of programming experience, it was actually homogeneous programming experience, where they had several sort of consistent levels of how much Python they had had before or other program. We asked a whole bunch of different questions to do that. And it wasn't a perfect situation. Each section had 16 people. So with all these constraints, it's like a highly over-constrained system. Yeah.
So it seems like there's this overwhelmingly positive comparison to traditional labs. But did you look at
Yeah, so the idea of comparing this to undergraduate research experience, and so lots of other people have looked at cures, many different cures, comparing that. We didn't have that data source. Yeah. Yeah.
So I'm thinking in the context of recent discussions we've had of another one of these one credit doctoral courses. I guess specifically advertised that like engaged in research experience. I think the big difference between those is that for 1400 is usually what coverage you presented this great example of how that it's really only effective when you have large
Yeah, I would. So actually, I mean, it's much more scalable if you have 30 students, right, to come up with a research question. It's actually much more challenging when you have so many students. The only examples of cures in physics are really at the upper division level, where there's 12 students in the course, and essentially they're doing research with individual faculty, but they're it's kind of like our honors course in some ways. So I think that's a much easier thing to do than the large intro courses, actually.
Yes, I'm wondering if there's a region of that primary space where it's small class, but also
Yeah, that's a question in terms of what research questions are most applicable there. Eric?
So you had sort of one level, which is the 3 or 4 students. You had the whole class of 300, but there was another pyramid that groups get together and
Yeah, so there were 16 students in a section with one TA, and so that they would occasionally meet in a room with 16 people to go over some various things, and then break out into breakout rooms, but the TA would then go around and hop between breakout rooms within that section, that sort of 2-hour section. Yeah.
So here it sounds like it's a great way of researching students without students. But at the same time, it's did it instead of conventional lab. Now, of course, that was the cause of potential, but going forward, students losing it by not maybe this becomes an additional.
Yeah, that's a great point. I think it depends on what goals you have for your students in that particular course, right? If it's learning how to use an oscilloscope, yes, I think that was not a goal of this course. I think it really depends on your individual goals and what trade-offs you want to make there. I would argue personally that these kinds of impacts, I mean, it's only one credit, like they sort of got what like real research was, like which is a struggle. They had a very positive experience that will continue on. I feel like that is a bigger impact than maybe making sure your resistors are wired up correctly. But that's my personal opinion versus data. Yeah.
Have you guys looked into how a research environment like this would impact students in the
Right, so that's a good question of like, when is the most applicable time to have this? And our hope, like going forward, is maybe at the sophomore level where they have a little bit more physics, but then that prepares them to be confident, understand the research process so that they can go on to do maybe undergraduate research or internships or other things. It better prepares them to sort of walk into another thing. So maybe that might be a place to look. You nailed it. I put that out to everybody else. If you have ideas of your own research, like, oh man, I have this project, man, it's kind of a side, but it'd be really interesting if I had 500 students work, or hold on, 100 students work on this for a few years, like, would that be useful? Please come talk to me. That is the key, right? And that's the struggle. And that's one of the big trade-offs. And how long you can go with that research question before you have to find a new one. 100% on board with that. Yeah.
Yeah, it's a delicate problem where finding success actually.
Yeah. It's just such, like, I feel like we've just got to try. Maybe we can't do it, but gosh, after this, I feel like we got to give it a go. Yes, I think this is the last question.
So I know you like early on like you had the goals like real research. I recall before
Yep.
I recall one of them was finding. I remember the other like
Basically, constructing the apparatus, designing the apparatus. Yep.
Right. So like I can see that you were more or less possible that person that those might be addressed.
I don't know. That's a good question. I think in cures, it depends on what, like there's a spectrum of cures, but often it's a little bit more defined or at least constrained, that part, but I think the more hands-on components can be brought in to the experience in particular.
No more questions. Let's thank Heather again.